You use vector every day. It just looks like a dynamically growing array. But here comes the question. What exactly happens when it runs out of capacity? Is it really just allocating a little more memory? How is the old data handled? Are objects copied or moved? Will an exception cause memory leaks? And why is vector so much faster than list? Today, we'll start with C++ to explore the sophisticated internal mechanisms of vectors. You'll find that what's going on inside a vector is by no means a simple realloc operation. In most compiler implementations, such as GCC's libstdc++, MSVC's STL, the internal structure of vector is actually very simple but extremely sophisticated. Essentially, it only has 3 pointers. Even for implementations in different compilers, the logic of these 3 pointers is completely consistent with no differences. The first pointer is begin, pointing to the start position of the vector data, that is, the address of the first element. The second pointer is end, pointing to the end of the used elements. Note that it is used, not the end of the capacity. That is to say, the area between end and begin stores existing data. The third pointer is cap. Some compilers call it end cap, pointing to the end of the vector capacity, that is, the position next to the last byte of the currently allocated memory. The size method you usually use is implemented as end subtract, begin at the bottom layer, calculating the number of currently stored elements. The capacity method is cap subtract begin, calculating the maximum number of elements the current vector can hold. Pushback within this range does not require expansion. Let's take a specific example. Create an empty vector. At this time, the 3 pointers are equal, and both size and capacity are 0. After pushback one element, if the capacity is insufficient, that is, end equals cap, expansion will be triggered. If the capacity is sufficient, that is, end doesn't equals cap, the new element is directly constructed at the position pointed to by end, then end is moved backward by 1 bit. There is no extra overhead in the whole process. And all the really complex logic lies in the moment of expansion. Suppose we only increase by 1 each time we expand. What will happen then? Each pushback requires 3 operations. Allocate a new memory block 1 larger than the original, copy all old elements to the new memory, and then release the original old memory. In this way, the time complexity directly becomes O(n squared). So vector will never do this. It adopts a geometric expansion strategy. Different compilers have different expansion multiples. GCC's libstdc++ uses 2 times expansion, and MSVC uses 1.5 times expansion. Why is there such a difference? The core is the balance between memory utilization and expansion times. 2 times expansion has fewer expansions and fewer total copies, but it is easy to waste memory. 1.5 times expansion has higher memory utilization, but there will be more expansions and slightly more total copies. But no matter which multiple, the core purpose is the same, to make the total number of copies linear and the amortized time complexity reaches O(1). That is why when you use vector, usually you do not feel the cost of expansion and think it has almost no overhead. But at the moment of expansion, the cost is real, but it is averaged into each pushback operation. Let's take a specific example combined with libstdc++'s 2 times expansion strategy. Suppose the current vector capacity is 4 and size is 4. You want to push the 5th element, triggering expansion. The whole process is divided into 5 steps. Step 1. Calculate the new capacity. There are 2 details here. If the old capacity is 0, empty vector, the first expansion will not directly use 2 times, but a default initial capacity will be allocated. Different compilers are different. libstdc++ defaults to 1, MSVC defaults to 4, and some compilers default to 2. If the old capacity is not 0, calculate according to the geometric strategy, such as 4 times 2 equals 8. The new capacity is 8. If the calculated new capacity is still smaller than the minimum capacity currently required, such as using resize 10 when the current capacity is 4, 2 times expansion to 8 is still not enough. The new capacity will be directly set to 10. Step 2. Allocate new memory. This step is one of the core overheads of expansion. Vector will not apply for memory by itself, but call the internal allocator. Vector will call the internal allocator, that is, the allocator, to call allocate. This step will eventually go to operator new, then to malloc, and finally to the system call brk or map. That is to say, the expansion of vector is essentially applying for heap memory at the operating system level, which itself has a certain overhead. Step 3. Construct the old elements in the new memory. This step is the most critical step. Many people think that memcopy is used to copy the old memory data here. In fact, it is not. When vector expands, it is not moving memory, but constructing new objects and destroying old objects, complete object lifecycle management. Specifically, vector will call one of the following 2 functions. Whether to use move or copy depends entirely on whether your element type has a noexcept move constructor. If the element type has a noAcceptMove constructor, vector will call uninitializedMove to move the old elements to the new memory. Note that it steals the resources of the old elements. The old elements will become empty shells but will not be destroyed, which is extremely efficient with almost no extra overhead. If the element type does not have a noAcceptMove constructor, vector will fall back to uninitialized_copy and honestly copy the old elements to the new memory. Copying is a deep copy which will reallocate resources and is inefficient. Why must vector check noAccept? Because vector must guarantee strong exception safety. If the move constructor may throw exceptions, then during the process of moving elements, if an exception is thrown halfway, the elements in the new memory are not fully constructed, and the elements in the old memory are damaged, resulting in data confusion and memory leaks. So vector would rather give up efficient move and use safe copy? Even if the efficiency is lower, it must ensure data security. Step 4. Destruct the elements in the old memory. After all old elements are successfully moved or copied to the new memory, vector will call destroy, traverse all elements in the old memory, call their destructors one by one, and release the resources occupied by the elements themselves. Step 5. Release the old memory. After destructing the old elements, vector will call the deallocate method of the allocator to release the old memory and return the old memory to the operating system. Here, the entire expansion process is completed. You see, this is not simple memory handling at all, but a complete resource management process from memory allocation to object construction to object destruction and to memory release. Another question, why is vector faster than list? The core advantage of vector is continuous storage. All elements are closely adjacent and stored in a continuous block of memory. First, the cache line utilization is extremely high. When the CPU reads memory, it loads adjacent memory data into the cache together. Vector stores continuously. After accessing one element, the next element is probably already in the cache, and the cache hit rate is maximized. Second, the CPU prefetch mechanism takes effect. The CPU will predict that you will access the next element next, load the data into the cache in advance, and further improve the speed. Third, the TLB hit rate is high. TLB is a cache from virtual address to physical address. Continuously stored memory is mostly in the same or adjacent memory pages. As long as the TLB hits once, subsequent accesses can be reused, greatly reducing the overhead of TLB miss. Each node of list is allocated memory separately, and nodes are connected by pointers. The memory distribution is random and scattered. This will lead to frequent cache misses. Every time the CPU accesses the next node, it has to go to a new memory address. There is nothing in the cache, so it can only read from memory, which is very slow. There are also many TLB misses. Each node may be in a different memory page, and the TLB cache fails frequently. Moreover, it will cause CPU branch prediction failure. The CPU predicts the wrong pointer jump direction and has to repipeline, which consumes extra CPU cycles. Finally, here is a performance optimization tip in actual development. If you know in advance how many elements the vector will store, you must call the reserve function in advance. What can this step avoid? Avoid multiple expansions. Avoid multiple memory allocations, element copies, and destructions. Especially when the elements are complex types, the performance gap may be orders of magnitude. Therefore, vector is never a simple dynamic array. It is the intersection of C++, object model, memory model, and CPU hardware behavior. If you're also interested in C++ and computer low-level mechanisms, you can click follow. See you next time.